Hi everybody, you are very welcome to this third session of a series of webinars dedicated to data science. Today we'll be talking about statistical testing, which I will illustrate with the XLSTAT software, which many of you already know. Otherwise, this will be a good opportunity to learn more about it. But statistical testing is a very broad topic, so unfortunately we won't have the time to speak widely about it today. We only have 1 hour. So I really hope you'll get the sense of how statistical testing works and how to implement basic statistical tests in XLSTAT. Now, if you want to go further in statistical testing, I would advise you to do some more research or follow some specific tutorials or ask for specific trainings from XLSTAT. So XLSTAT is developed by the Addinsoft company, in which I work as a data science consultant. At the end of this webinar, there will be a Q&A session in which I will be answering your questions. So don't hesitate to submit your questions in the chatting window. I will try to answer as many questions as I can at the end. You should know that there will be a recording available and you'll receive a link to this recording within a few days. If you think there are colleagues who could be interested by the webinar and who weren't able to connect today, you'll be able to send them the link. Also, there are handouts that you can download, as well as the data that we'll be using to illustrate this webinar and run demonstrations. So there should be a button somewhere on the webinar platform in which you can download these elements. So let me start with an outline. What will we be talking about today? I'll start by saying a few words on XLSTAT, then presenting my usual way of dividing statistical tools into several families of tools. Then I will present a reminder of what we've already seen in the two previous webinars, so what we've seen last week in terms of data description and exploration. And after that, I will start talking about statistical tests. So first, I will start with principles, the different steps in the procedure of statistical testing, and we'll implement our first test together, which will be a comparison of two means. After that, I will tell you what the difference is between parametric and non-parametric tests, then the difference between comparison and association tests. And after that, we'll be applying an association test between two qualitative variables and an association test between two quantitative variables. You should know that I've added a couple of appendices to this PDF. So how to interpret a p-value which is larger than alpha. We'll be talking a lot about this number here, the p-value, and what the difference is between independent and paired samples. Unfortunately, I won't have enough time to talk about these today. So who are we? XLSTAT is a statistical software that works as an add-on to Excel in PC and in Mac. It's also available for Excel 365 and Google Sheets, so on the cloud. So one of the main strengths of XLSTAT is that it works on Excel. So all the analysis process from capturing your data to the customization of your results passes through Excel. You really don't need to use another interface in the analysis process. So this makes the software very user-friendly. In a few numbers, XLSTAT has more than 220 statistical features, more than 150,000 users worldwide, more than 25 employees at your service, and 300K monthly visits on the website. It's available in 7 languages and 3 time zones across the globe. So we have offices in America and Europe, as well as in Japan. There are 10K monthly downloads of the software. XLSTAT is established in the Data Factory, which is a lab located in Bordeaux, France, and which holds 5 expert companies around the world of data. It's very active in terms of data science, as it organizes more than 25 workshops, events, and trainings every year. XLSTAT proposes or offers 8 solutions to meet your specific needs. So first of all, we have 3 generalist solutions, which are basic, basic plus, and premium. Basic offers 100 essential statistical tools which allow exploring, visualizing, and modeling your data in one single interface. Then Basic Plus has all what Basic offers, plus machine learning features. Premium contains the complete 220 XLSTAT features. Then between Basic Plus and Premium, you have intermediate solutions which are field-oriented, such as Sensory for experts in sensometrics and for product optimization in terms of sensory attributes. Life Sciences for biostatisticians and agronomists and researchers in the medical field. Marketing for market research and strategy. Forecasting for the analysis of time series and risk analysis. And at last, Quality for statistical process control and quality control and design of experiments. XLSTAT has more than 200 tutorials associated to downloadable data sets on this link here. So you can click in the PDF on this image here and you will reach the page of the XLSTAT tutorials. You should know that every feature in XLSTAT has one specific tutorial online that guides you through all the process from the configuration of the XLSTAT dialog box to the interpretation of the results. So you have a lot of resources online to train yourself on using XLSTAT. Also, we have a Stat Cafe YouTube channel, which proposes short format videos which explain different features with applications using real data in XLSTAT. So here are the 4 families of tools in which I classify the different statistical tools to deliver these webinars. So first of all, we have descriptive tools describing data, which allow to describe one variable or the link between 2 variables. So we talk about univariate or bivariate statistics. This was the topic of our first webinar last week. We talked about the mean, the standard deviation, histograms, box plots, and the scatter plots, and so on. Then data exploration and clustering tools allow to easily extract information from wide data sets without necessarily having a precise question to answer. So these tools include PCA, or principal component analysis, and agglomerative hierarchical clustering. This was the topic of the second webinar last week. Today we'll be focusing on this one, statistical testing, which allow to accept or reject a very precise hypothesis, assuming error risks. So we'll mention the t-test, the chi-square, correlation test. So these tools allow answering questions whose answer is yes or no, as you'll see. And at last, statistical modeling allows to understand how a variable behaves according to a set of other variables and optionally make predictions. You can access recordings of the 2 previous webinars through these buttons here, these links. Okay. Otherwise, if you'd like to subscribe to the upcoming webinars around statistical modeling, I have included some links here as well. So one link for statistical modeling and regression, and another one for ANOVA. Here's a small reminder on data description and exploration. So reminder of what we've seen last week. We worked a lot on this data set, which is in Excel here. And it's an online shoe selling platform, so it consists of clients of an online shoe selling platform, which are stored in rows. So you have individuals or observations in rows. And these observations or individuals are characterized by what we call variables. So variables can be either quantitative, so expressed in terms of numbers, such as height, shoe size, weight, time spent on site, and invoice amount. They can also be qualitative or nominal, such as origin, gender, preferred brand. Okay. And in most cases, data sets are organized this way, so with observations in rows and variables in columns. We've seen different tools to describe one single qualitative variables, one single quantitative variables, then the link between 2 qualitative, 2 quantitative, 1 quantitative and 1 qualitative variables. And at last, we had investigated this case how to check or to describe the link between three variables, two quantitative and one qualitative. And I just wanted to get back to this special case here to show you what we've done. So how to describe the link between three variables. This is one of the ways. I have displayed a scatter plot with one quantitative variable on Y, this is the invoice amount, another one on X, the time spent on site, and I colored the different points according to the qualitative variable. And starting from this chart, this simple chart, I was able to extract a lot of interesting information. I see that globally invoice amount decreases with time spent on site, which is not necessarily the case within each group. Then Plutonian customers, so the gray ones, spend less time on the site compared to the others. Customers from Earth and Mars form a homogeneous group, so at the bottom right. So these hypotheses, I was able to extract them from a simple chart. And this kind of reasoning was generalized in data exploration, which was the topic of the second webinar, and in which I presented tools which allow to summarize the information from wide data sets in very simple charts, in few charts. So we've talked about what we call PCA, or principal component analysis. So this principal component analysis summarizes the information of 4 different variables: time spent on site, shoe size, weight, and height. We've seen that to interpret the link between two variables, we should check the angle that separates them. So a short angle or a small angle, such as between weight and height, shows a positive relationship. So when height increases, weight increases. And in the opposite, wide angle shows a negative relationship. So when weight increases, time spent on site decreases, for instance. And the right angle shows no relationship between the variables. And we've seen that we're able to characterize the observations according to the variables. So here, if we check the observations to the right, we can characterize them by high scores of variables that go to the right, so high scores of weight and height, and low scores of variables that go to the left, so time spent on site. And here, the opposite. Observations on the left are characterized by high scores of time spent on site and low scores of weight and height. So for more details about this, I suggest that you check the recording. So all of these hypotheses, I was able to extract them from my PCA analysis. But what I stressed on last time is that the decisions you make, or the information you draw out of an exploratory tool, cannot be said in a very firm way. So what will really help you make decisions and measure the amount of risk you are taking of being wrong is statistical testing. This will be the topic of today's webinar. I will start with the principles of statistical testing and the different steps I suggest you to take if you don't really have experience in statistical testing. Now, you should know that quite often statistical test outputs or outcomes are misinterpreted in the literature. So please be very careful when you interpret a p-value or when you interpret a risk threshold. Statistical tests are used to accept or reject a precise hypothesis, assuming error risks. As I told you earlier, they allow answering questions whose answer is yes or no. So we'll first develop a step-by-step procedure that goes from the question to the interpretation of the result, and we'll pass through the implementation of the test in XLSTAT. So this is the step-by-step procedure I suggest you to follow. So we start by stating a question whose answer is yes or no. After the question, we write a null and an alternative hypothesis, so you will know what each one of them is. Don't worry, there are a lot of weird terms in this list. Don't worry, we'll be developing each step aside. And then we choose an appropriate parametric test. We set an alpha risk threshold. We gather the data. We verify the conditions of validity of the test, and if they are not met, one suggestion, one solution would be to switch to a non-parametric equivalent. We run the test, and if the p-value which is provided by the test is lower than alpha, we reject the null hypothesis. So let's develop each step aside. We start with an example. Imagine we want to study the influence of a new education system on student grades. So on one side, we have 30 students who follow a program with the former system. And on the other side, we have 30 other students who follow the education program with the new system. Then at the end, their general grade over 20 is recorded. So in total, we have 60 students, 30 undergoing the current system and 30 others undergoing the new system. The question we ask is there a significant difference in the mean grade between students who follow the program with the former system and those who followed it in the new one? So is the new system more performant or less performant than the current system? So we'll establish a statistical testing procedure to answer this question. So I will show you just a teaser of the result before developing each step aside. So this chart represents the mean grade on the y-axis for each of the two systems, so the former one and the new one. Here we see that the new one has a higher mean grade than the former one. And let us focus on this element here, which we call the p-value. The p-value is a number provided by any test and represents, in a way, the risk you take of being wrong while saying that there is a significant effect of your system, your new system, or there's a significant difference between the two means. Now, this is not the real definition of the p-value. The real definition of the p-value is a little bit complicated, but this gives you a little bit of sense of interpretation of the p-value. So I think that if there are statisticians listening to me, maybe they won't be very happy, but I didn't give you the precise definition of p-value, but an alternative one. So p-value is the risk you take of being wrong when saying that there is a significant effect, here a significant difference between the two means. So here you can see that the risk is very, very low. So you may say that there is a significant effect. Let me take back the different steps I've exposed earlier. So I need to write down the null and the alternative hypothesis. So each statistical test is associated to one null and one alternative hypothesis. Here is how we can write down the null hypothesis, which generally implies an idea of equality. So the null hypothesis, or H0, can be written as such: the mean of the former system equals the mean for the new system. The alternative hypothesis, or HA, generally implies an idea of a difference. So the mean of the former system is different from the mean of the new system. So those two hypotheses are opposed to one another, and the statistical test will allow us to test the null hypothesis and leads to a decision of rejecting it or not. And if we ever reject the null hypothesis after the statistical test computation, we can accept the alternative hypothesis while taking a certain amount of risk of being wrong. So now that we've written the question, the hypothesis, we need to choose a statistical test, an appropriate test. If you go and explore the different statistical testing menus in XLSTAT, you will notice that there are many. So which one should you be using? You can examine the hypothesis and the question and try to translate them in terms of statistical terms. So are we comparing means? Are we comparing proportions? Are we comparing variances? Are we testing the association between two variables? I think you all agree with me that we are comparing means, and we are comparing two means. And starting from this, if you don't really have experience in statistical testing, you can use statistical test guides. For instance, one which is right here. So this is a list of statistical tests you can use based on the question you are asking and the null hypothesis. So don't hesitate to use this grid to choose the appropriate test. I have included in your PDF a small version of this grid that includes very commonly used tests. If you look at the question here, you can already recognize our problem. We are comparing two means. Then, based on this, you can choose whether your samples are independent or paired. Unfortunately, I don't have the time to tell you enough time to tell you what the difference is between both today, but just trust me, our samples are independent in this case, so you can use a student's t-test on two independent samples. We will see what the difference is between parametric and non-parametric tests. So we've set the hypothesis, we chose our test, and now we need to set the alpha risk threshold. So this slide is quite tricky, okay? The alpha risk threshold is the threshold below which we allow ourselves to make a decision, and its value is bounded between 0 and 1. So this is a probability value. So you as a user should be choosing your alpha risk threshold. It's not the software that computes the threshold for you. You need to choose it according to the amount of severity you want to put in making a decision or not, how conservative you want to be. So alpha should be determined according to how dangerous it is to reject H0 while it is true. So say you work in healthcare and that you need to make a decision out of an experiment, and you prefer not taking a decision instead of taking a one which is possibly wrong, because taking a wrong decision would lead to disastrous consequences. So if you prefer being conservative and making a decision or taking a decision only if the effect you are observing is very strong, then you should decrease alpha. But if it's better for you to take a decision while assuming a higher risk of being wrong, you can increase alpha. So you really need to think about this while setting your alpha threshold. Now, very often people set alpha at 0.05, but this is not a reason to do it systematically. This is one of the misuses of statistical testing. But this is the threshold we'll be using in our examples. So alpha is the risk threshold to which we will be comparing our p-value, as you will see. Then we gather the data, and they are in the education Excel sheet, and the data I sent you. So each row corresponds to a student. So some students were submitted to the former system, and other students were submitted to the new system. As you can see, if we display a box plot of the grades, we see that for the new system, we have values which are higher than the current. So we may expect that we would obtain a significant difference between the two groups thanks to the test. So we gather the data. There's something important we should verify before launching the test. So classic tests or parametric tests are only valid under certain conditions. So for instance, the conditions of validity for students' t-test for two independent samples, which is the test we chose before, is only valid under these conditions. Measurements should be independent, which means that in your data set, each student should be associated to one single measurement. Then group variances should be equal. So the variance of the group of the former system should be equal to the variance of the group from the new system. Then you need to have at least 30 individuals per group, or you have to verify the normality for each group, to assume it or to verify it. So either to verify it or assume it based on the literature, for instance. And what is normality? The normality of a series of quantitative data is a bell-shaped distribution of these data. So conditions of validity for parametric tests can be checked here on this link. So this is the big guide I showed you before. You will see all the conditions of validity for each and every test. So don't hesitate to check them out. So how to run student's t-test in XLSTAT. So I will go to test the hypothesis and click on parametric tests. This is where I will find my student's t-test for 2 independent samples, which is hidden inside this feature here. 2 samples t-test and z-test. This is a typical XLSTAT dialog box in which you have different tabs that you can configure and that you can fill out with data. First of all, you need to select the data format you are selecting. Here, do we have 1 column per sample? Do we have 1 column per system? Or do we have 1 column per variable? We rather have 1 column per variable. So the other format corresponds to this one, and I wouldn't recommend this format. So if the 1 column per sample format corresponds to this one. So we have 1 column for the grades from the former system, another one for the new system. So I will stick to 1 column per variable and select the data here. So these are my data, and my sample identifiers are in column A. Okay. In the options tab, I can set the alpha risk threshold. So here I set it in terms of percentages. So 5% means 0.05. Then in the charts tab, I can activate comparison plots, such as bar charts with error bars. And here I just take standard errors and show p-values. I will focus on the p-value. So this is the main number we'll be talking about in the test result, and that I will be commenting on the presentation. So here I wrote back the question, the null hypothesis and the alternative hypothesis, and I got a number called p-value out of the test. The p-value is a probability value, so it's bounded between 0 and 1. So how to interpret this p-value? You need to compare it to the risk threshold alpha. If the p-value is lower than alpha, you reject H0 and accept HA, assuming a risk proportional to p-value of being wrong. So the lower the p-value, the lower the risk you take of being wrong while rejecting the null hypothesis. So in other words, if your p-value is lower than alpha, you have a significant effect. So in this case, you choose the alternative hypothesis. But if the p-value is higher than alpha, normally you cannot make a decision. And I give you a hint of further interpretations of this output in the appendices. So here my p-value is very low compared to alpha. So we can reject H0 and accept HA and answer the question. The 2 education systems result in significantly different grade means, and the risk of being wrong when stating this is lower than 0.0001. So this is the way the student's 2 sample t-test works. So I won't get into the details of this formula. And there are other things, of course, it's important to look at when we run statistical testing, such as size effects. So sometimes you can have like very significant results, so a very low p-value, but actually which is linked to a very slight difference in means, which wouldn't be very interesting in terms of introducing, for instance, a new system of education. Which is why I recommend always having a look at the data and not only rely on the interpretation of the p-value. Now, of course, to obtain this chart, as you saw, I have activated these different options. And sometimes in the literature, you find this kind of charts in which you have the means and the p-value displayed on the chart. So XLSTAT provides you with this chart automatically. What's the difference between a parametric and a non-parametric test? So this is a matter of power versus robustness. So you should know that non-parametric tests are more robust and parametric tests have more power. So this would be the main message of this part of the webinar, but let me get into the details now. Now, a statistical test can be parametric or non-parametric. Parametric tests are reliable only under certain conditions linked to the distribution of the population. So we saw that for students' tests for 2 independent samples, we need to have equal variances and we need to verify the normality of each group if we have less than 30 individuals in each group. On the other hand, non-parametric tests do not assume any underlying distribution, and most of them are computed from the ranks of the data. So non-parametric tests are valid in a wider range of situations. So the question we may ask, why do we still run parametric tests and we still try to check the validity assumptions? Why don't we just run non-parametric tests which don't really impose this constraint of verifying validity assumptions? So non-parametric tests, as I told you, are valid in a wider number of situations. So we say that they are more robust. On the other hand, parametric tests are more able to reject H0 if it's wrong, and if, of course, conditions of validity are met. So we say that parametric tests have more power. So parametric tests would lead more often to a reject of H0 or to a decision in your test compared to their non-parametric equivalents. So how to incorporate this in the step-by-step procedure? So in this step, you verify conditions of validity of the parametric test. If they are not met, you switch to a non-parametric equivalent. So this would be one solution to implement. Of course, there are other solutions, but I won't have the time to talk about them today. Let me show you how to run a non-parametric equivalent of students' t-test for 2 independent samples. So I'll be running a Mann-Whitney test on the data we are working on. So this one. So I will go to test the hypothesis, non-parametric test, comparison of 2 samples. Once again, I need to choose the appropriate data format I am inputting. I have 1 column per variable. So I will select my data here, my sample identifiers here. And here, as you can see, XLSTAT automatically takes Mann-Whitney's test. I can configure my significance level here, and I can also display charts, which I can configure in this tab. Once again, I obtain a p-value, which leads us to the same conclusion. So there is a difference in location between the new system and the current system. So we talked about the difference between parametric and non-parametric tests. In a nutshell, if the conditions of a parametric test are met, stick to the parametric test because it has more power. If not, one solution would be to switch to a non-parametric equivalent, which you will find in the statistical testing guide I showed you. Now, what is the difference between association and comparison tests? So comparison tests imply comparing statistical measures, such as comparing means, and these include students' t-test and ANOVA, comparing variances, such as Fisher's f-test or Levin's test, comparing proportions, proportion tests, for instance. So there are tests for each of these cases. On the other hand, you can also test the association between 2 variables. For instance, you can test the association between 2 qualitative variables. And here we'll run tests on contingency tables such as chi-squares or Fisher's exact test. You can also test the association between two quantitative variables, such as Pearson's correlation coefficient test and Spearman's correlation coefficient. So Pearson is parametric, Spearman is non-parametric. So I will take each case here and develop one example of each. I will start by testing the association between two qualitative variables, and I will consider this example, the Titanic data example. So does survival of Titanic passengers depend on their travel class? So in this table, we have the survival of passengers in rows and the class of the passengers in columns. And this is a crosstab or a contingency table. So each cell represents the number of cases corresponding to the two corresponding categories. So I have 122 passengers from first class who did not survive. I have 118 passengers from second class who survived. So this is the contingency table format of the link between two qualitative variables. Here is how I can write down the null hypothesis and the alternative hypothesis. In the null hypothesis, the rows and the columns are independent, so survival does not depend on class. And under the alternative hypothesis, rows and columns are dependent, so survival depends on class. Now, how can we check this just by looking at these numbers? How can we know that survival depends on class? Maybe looking at the row data does not really help. Why don't we measure the percentage of survival within each class? Look what we obtain. So in the first class, we have 62% of survival. In the second class, we have 41%. And in the third class, we have 25%. So very clearly, survival depends on the class. So we may expect that we would reject the null hypothesis and accept the alternative hypothesis. And I had told you also that the null hypothesis often implies an idea of equality. So I can write it down in another way. I can say that the proportion for class 1 equals the proportion from class 2 equals the proportion from class 3 in the null hypothesis. Under the alternative hypothesis, we may say that there is at least one proportion which is different from another. This is another way of writing down the hypothesis. So one of the tests we may use, according to our guide, to answer this question is the chi-square test, very famous test. So let me run it for you in XLSTAT. So test the hypothesis, correlation and association tests, and tests on contingency tables. First of all, I need to choose my data format. Do I have raw qualitative variables, or do I have a contingency table? In this case, I have a contingency table. So raw qualitative variables would have been like two columns, one column for survival, another one for class, and each row would have represented one passenger with the information of survival and class. So I will just stick to contingency table and capture my contingency table here. In the outputs, I can ask for the percentages per row and percentages per column, which could be interesting. And in the options, I can choose a test I want to investigate. So as you can see, we have many tests for the contingency tables, and they all more or less answer the same null hypothesis and alternative hypothesis. But the chi-square test is the most common one, but it has some constraints, it has some conditions of validity. But the Fisher's exact test is a kind of non-parametric equivalent from the chi-square test. So I will just activate it, and we'll investigate the results of both. Here's the result of the chi-square test and the associated p-value, which is very low, so it leads me to a reject of the null hypothesis and an acceptance of the alternative hypothesis, which states that survival depends on class. Here's the result of Fisher's exact test, which also leads to the same conclusion. Now let me test the association between two quantitative variables. I will get back to this data set of the online shoe selling platform and ask this question: are there links between variables in the frame taken by pairs? I will be illustrating things using Pearson's correlation. So I will take each pair of variables apart and test the link between the two variables. Is there a link between height and shoe size, a link between shoe size and weight, between height and time spent on site, and so on. So what can I do? First of all, I can compute what I call a correlation coefficient. So, for instance, Pearson correlation coefficient, which measures the strength and direction of the linear link between the two quantitative variables. So between each two quantitative variables, I will compute this R index here. And here is how I can interpret this correlation coefficient. This coefficient ranges between -1 and +1. If the coefficient is close to -1, there is a negative correlation between the two variables. So when one increases, the second one decreases. If the coefficient is close to +1, there is a positive correlation between the two variables. So when one increases, the second one increases. If the correlation is close to 0, there is no correlation. So when one variable increases, the other one is not affected. Now, based on Pearson's correlation coefficient, we can formulate or we can write down hypotheses. So under the null hypothesis, we can say that the coefficient is null, so there's no correlation. Under the alternative hypothesis, we can say that the correlation is significant or is different from 0. This is one way of writing down null and alternative hypothesis. Now let me run the test in XLSTAT. So I will go back to this data set, CRM, then test the hypothesis, correlation and association tests, then correlation tests. First of all, in this field here, I will capture all the data I want to run the correlation tests on. So these are these 4 columns. So XLSTAT will automatically take all the pairs, each pair apart, and run the correlation test on each. Here I can select the type of correlation I want to compute. Pearson is parametric, and all the other 3 are non-parametric. I have my significance level here. I can configure the percentage once again. Then one recommendation, if you ever run correlation tests in XLSTAT, I will strongly advise you to select the pairwise deletion and the missing data tab if you have missing data in your data. In the outputs, I will activate correlation coefficients, of course, and p-values. And in the charts, I will activate scatter plot and matrix of plots. So I would advise you to activate this if you don't have a lot of columns to investigate. Here I only have 4 variables or 4 columns I'm investigating, so I can activate this option. Otherwise, the computation time would be too long, and the chart that you would obtain would be a little bit too fuzzy to interpret. So we obtain something we call a correlation matrix. There it is. Okay. I will comment on the correlation matrix in the presentation. So the correlation matrix shows you the different variables in rows and the different variables in columns as well. Each number corresponds to the correlation coefficient between the 2 variables that are taken into account. So for instance, the correlation coefficient between shoe size and time spent on site equals 0.35. Correlation coefficient between height and time spent on site equals minus 0.64. And as I told you, how to interpret the correlation coefficient. When the correlation coefficient is close to 1, which is the case between weight and height, then the relationship is positive. So when height increases, weight increases as well. When the correlation coefficient is close to -1, such as depends on height versus height, we have a negative correlation, negative relationship, which means that when one variable increases, the other one decreases. Now, you can see that there are a few numbers that are displayed in bold. What does this mean? This is the result of the statistical test, which is behind. So when the correlation coefficient is displayed in bold, this means that the correlation coefficient is significantly different from 0. So this means that we reject the null hypothesis for this specific correlation coefficient. So for instance, if we take this coefficient, we have a significant negative correlation. So height increases when time spent on site decreases. Then this one is positive, but is insignificant. It's not displayed in bold. So although we have a positive correlation coefficient, this positive relationship is not significant. So we did not reject the null hypothesis for shoe size versus time spent on site. So this is how we interpret the correlation matrix. And you can notice that the matrix is symmetrical according to the diagonal. So you get the same numbers here and here. So before summing up, I just wanted to show you the scatter plot matrix, which is provided by XLSTAT and which is very, very important. So as you can see, here again, we have the variables which are displayed in rows in this matrix, as well as in columns. And each chart represents a scatter plot between the two corresponding variables. So here, for instance, in this chart, we have height on Y according to shoe size on X. Here we have height on Y according to weight on X. So this allows you to investigate all the relationships visually between the variables and possibly to detect like outliers or weird patterns in your data. Every time you run a statistical test, don't just go directly to the interpretation of the p-value. Be careful about the data behind. Sometimes one correlation coefficient can be totally driven by one specific outlier in your data, and which would lead you to very wrong decisions or answers to your question. So please do check your data before running any statistical test. So to sum up, here's the step-by-step procedure we followed. We went from writing the question to answering this question, and we passed through setting the null and the alternative hypothesis, choosing an appropriate parametric test, setting the alpha risk threshold, gathering the data, then verifying the conditions of validity for the test, and if they are not met, switch to a non-parametric equivalent, running the test, and interpreting the test based on the p-value and alpha, and rejecting the null hypothesis if p-value is lower than alpha. But always be careful, as I just said, to look at the data before interpreting the p-value. So this is the guide I had shown you before. There's a specific test here, the ANOVA, which is statistical model also, that we'll be investigating in the upcoming, not the upcoming webinar, the one after, so next week on Tuesday. ANOVA allows to compare several means. So it's a generalization in some way of students' t-tests for two samples. Okay, so I have included this slide, which allows you to access the recordings of the two former webinars and to register to the upcoming webinars. Right after that, you have like an appendix to see how to interpret a p-value higher than alpha and what is the difference between independent and paired samples. So let me take your questions now. So I have a question on the conditions of validity for students' t-test. Somebody is asking, group variances should be exactly equal or say similar. So let me get back to this slide. Yeah, these are the conditions of validity for the students' t-test for two independent samples. I told you that the group variances should be equal. One of the ways to verify this is to run a test that compares two variances. And this can be run in XLSTAT. Let me show you how. Here we go. I will run a test to compare the variances between the two systems. So I'll go to test the hypothesis, parametric tests. As you can see, you have tests that allow comparing two variances, so two sample comparison of variances. I will select my data here and my sample identifiers here. We run a Fisher's F test, which is one of the most commonly used tests to compare two variances, and click OK. And as usual, I will obtain a p-value. A p-value which is associated to hypothesis H0 and HA. So let me write down the hypothesis in another way here. So here the H0 can be written as such, where variance 1 equals variance 2, and HA is the opposite, so variance 1 is different from variance 2. Okay. Check out this p-value. The p-value is higher than the risk threshold alpha, so you cannot reject the hypothesis that says that the variances are equal. So in this case, you are happy and you can carry on by running your tests if the other conditions are verified, of course. About the correlation graphs, could you show us the ones with significant positive and negative correlations? So I will just copy and paste this correlation matrix here. So where are the positive significant correlations? Look here, height versus weight is very significant and is positive. You see it here. Then time spent on website versus height is negative. You have a negative relationship here. You have a gap in between, so maybe you should be asking yourself why there's a gap. Otherwise, there's this relationship also that appeared. So this is the relationship between time spent on site and weight. So weight, and there it is. So this relationship is also negative. Are Pearson correlations displayed as lowercase r, or is that r square? Well, Pearson correlation coefficients do not correspond to r square. The Pearson correlation coefficients can take negative values, whereas r square values are bounded between 0 and 1. And we will see r square in the modeling webinar, so next Thursday, and we'll see how to interpret r square. But no, the Pearson correlation coefficient does not correspond to r square. I want to compare preference results between 3 cities. Which method should I use? Let me take this one. Say we don't have origins here, but we have cities. We have 3 cities, Mars, Pluto, and Earth, and customers coming from these different cities. And these customers have rated their preference of a certain product. They rated the preference over 200, say. Okay, and how can we compare the mean preference across cities? We have 3 cities, so we have 3 means to compare. If we go to the statistical guide that I showed you here, if you want to compare k-means, we can use ANOVA, or analysis of variance, and this will be the topic of the webinar next Tuesday, next week. Thank you all for participating to this webinar. I really hope you enjoyed it, and I hope we'll be able to talk to each other again next Thursday. We'll be talking about modeling. Thanks again, and goodbye.